Hello. Why you gotta ask me questions like that?
Why you
Get out of
gotta
my space. Get out of my padded cell, bro.
Your padded self. How's you?
Good. Got a llama on the screen. Could be worse.
You're so cute.
I'm tired. I don't know why I'm tired all the time.
Well,
Like
you have a newborn.
Yeah. And a 3-year-old, that's also more tiring than newborn. Like last night I looked at Christina, I was like, I can play video games or we can go get in bed. Literally just opened our shades to our windows and watched the storm and we're in bed by 8.
Nice.
We're just like, I didn't go to bed until like 10, but still. Just I was just like, kind of feel like I just want to lay here and do nothing. As opposed to sit there and play games to do nothing, but whatever.
That's nice.
Yeah, I also had lunch right before I had this, so I'm tired.
You had what?
Lunch.
Oh. Cook home.
Yup.
Okay.
Turkey sandwich, some pretzels on cheese stick.
Delicious.
Topo Chico.
Delicious.
Yeah, it's busy. Bubbles in my tummy. Yeah, so I didn't see anything crazy because you're just straightforward all those others do. And now not doing 5-2 makes it real easy. Not that 5-2 was difficult. One less thing.
Yeah, I went back and watched it and I was like, actually I don't even know where the laser pointer was and I don't think it matters. So I like messages
Is it detracting, distracting, or
yeah.
just silly? Nope. Okay.
I messaged him and I was like, can you watch this real quick and tell me? And he was like, I don't even remember where it was. I was like, okay, cool. We're
Bro, that
done
was like
with
4
it.
months ago.
I know.
I think you go into rinse out. I'm gonna have to go do that. You go rinse out my coffee cup and put a Dr. Pepper in there.
Okay.
I'm gonna need something.
Okay.
I'm fading fast.
I'll press all the buttons. Sorry.
Okay, thanks. I'm gonna turn off all the lights. And play some ocean music. And just deep thoughts by Drew. Close your eyes.
Oh man, I'd love to.
There's a shark! You're gonna die. Jimmy Fallon. Roar forever.
Oh, do you want water?
I brought some drink.
Oh, nice.
Better, which is good because she tried to like bust it up again, but fortunately she did not succeed.
She seems skilled at that.
Yeah. She does like to go rather hard.
Is she back playing Ultimate?
Sort of. She's playing, but not at full capacity. She doesn't want to re-injure it while it's still technically healing, so. But she is playing again, which makes her very happy.
Does she get paid to do that?
Sometimes technically, but it's like 40 or $50 or something. So it's like not really. I made the arguable mistake of CCing my chair on that email I sent about the grant calculations I was doing to other people that had all the like money saving for students and stuff. And now I'm in an email chain with a bunch of UFPR people because they're probably going to do a thing about it now. I was like, well, that wasn't really my intent. Ugh. Yeah, a year.
From what, like have to buy something?
Yeah, no textbooks and no online homework subscriptions in almost all of our lower division courses.
Yeah, I'd say that's a plus.
Yep.
I mean, to the students, I mean, whether or not it's to your, like, depends if the department was paying instead of the students. Would be a big key, but
Yeah.
this is a great idea, but not for the what stipend?
That's pretty much what I have a meeting with my chair tomorrow to discuss exactly that, because you have to figure out what the actual like infrastructure and salary impact was for that time period for UF, because they want to do stories and stuff about it.
No, that's good.
But-
it's like my first few years here, we built a studio and all like they're like, oh, by the way, you want a Spirit Accomplishment Award? And I was like, what's that? And then there's like 8 stages of it. And they're like, oh, you made it on to the next round. I was like, I don't know what that means. And like we were sitting up for like the first year of interface, I think. And the award bank was going on for that, but I didn't know anything about it. And Jolene, we had just crossed over, so Jolene had just become my boss, and she was like, "Dress nice," and I was like, "But we got to set up for the conference." So I was just dressed up nice and sweaty, and won one of the top 6 awards. Oh, hi! Thank you so much. At the time was head of that whole banquet thing, which someone was like, "Oh, it's in cahoots." But no, it was. He was like kind of sweaty, and I was like, "Thanks, son." Wasn't my plan. Jolene was like, "I'm just trying to get you more pants." That's pretty good. I'm wearing the shorts to set up. Every time you wear pants, I'm like, "What's happening?" It sounds horrible. What he means by that? Not anything else. Josh is gonna get me in trouble. Brenda and Kelly are both shaking their heads. I'm just like, yeah, well, that's true.
HR violations everywhere.
Yeah, it's fine. I love we get a new person because I get to throw them on the jacket.
Anyways, I think you should get a raise.
Yeah, yeah, right.
You could give me an extra $3,000 a year.
I'll just take 10% of what I save students. That's fine.
That would be great. That's like with the studio, it's like something that should have been like $300K, we got it done for like $100K. Bonus? I just worked for 4 years and actually don't show up.
Okay.
I retired. OPS. How do you have a team job and an OPS at the same time? Too many hours.
How do you have 10,000?
Not if you don't. Not me.
Okay. I'm going to my office.
All right,
Shout out if you need me.
will do.
You too.
I'll be like,
I'll just shout into the heavens.
help.
Just keep words back to me.
Just like,
Josh, I summon thee.
lights off and start strobing.
Like, nope, shutting down the light.
You've gotten there. Is this how many? You have like what, like 5 or 6 more shoots? How many more shoots are there? Quite a bit.
Yeah, we're only like halfway through
Yeah.
16 modules.
I just because I know we've done a ton there. Now we're doing a lot of module 1.
Yeah, because we sort of skipped module 1 initially, but we have like 100-ish, I think, videos that we're shooting.
They're all
So
super short, so we're
Yeah.
we're knocking out like 10, 12 at a pop.
yeah,
No, we're like up to module 8. We have to go to 16.
Yeah.
Okay. Like I said, you're one of my favorite professors, not just to record, but also just your general delivery and everything's awesome.
Thank you.
My hair.
But the students want to know. Same shirt. we literally had a professor, and she was like, I'm gonna wear the same shirt for all of my recordings. But she would come in for like 3 days straight at a time because she lived out. And literally by the end, she's like, I'm burning these clothes. I'm staying in the same clothes every single time.
Yeah.
And so she's like, the students are either gonna think that I only own this, or somehow I just timed it up correctly.
There we go. Josh, you put the brake in the wrong spot.
Oh no, really?
Yeah.
Josh!
Josh, I summon thee.
Hurry up, I hope you didn't go to the bathroom.
Yeah, the brake, like, this can come up together, but the brake was supposed to be sort of between these two with just the title, no, then blank, nothing on here. No, can you figure a way thing.
I'll have him come back in and fix it real quick. Oh, Josh. He said that he turned on some like background music. He said you said, Josh, I summoned thee, and the beat hit on the music.
Oh, that's fantastic.
Ooh, are you looking at it on your phone?
No.
Oh, it's saying you're seeing all my text even though you're in here.
Oh, I left you up on the computer.
Oh.
So there's supposed to be the break between these two. Like these can show up at the same time, but I wanted just like mathematical reasoning, nothing, and then click and have both of these come up.
Oh.
Do you see what I mean?
Yeah.
Just one of those things that I'm sure is a half-second fix for someone who actually knows anything about PowerPoint.
Wait, so you want this, then this? Oh, but this is together with this. This, then this?
Yep.
And that, and that, and that.
Perfect.
Okay.
Thank you.
Oh yeah, caffeine. Woo!
I've
Did you tell what I said?
already had 2 Red Bulls today, so.
Oh yeah.
Nice.
It's like I go into his office and I play like a dubstep remix of the Avengers theme because the picture he has in his office. And it's like dun 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 dun. And then when he makes me mad, I take it away. Dun, dun, dun. Oh,
It's just the end of every time you come out.
pretty much. We have a love-hate relationship. Phone on silent.
Yes.
Oh, sorry. Phone on
Released.
silent, not on vibrate on the wood table.
Well, it's on a nice soft leather padding, but you say this, and I'm going to make sure anyway. Because I'm all sorts of paranoid.
You know, that would happen to me as well. All right, quick sound check for me.
This is a sound check for you, so you can see and hear my sound.
You say now arriving.
Now arriving. I saw a video of a woman that does just a ton of voiceover work, including like that default voicemail sound.
Yep.
But she does like a bunch of gaming and stuff. And so
really?
she was like doing, some gaming on voice chat with random people. And they're like, your voice sounds familiar. And she's like, yeah, I do some voiceover. And they're like, what? And then she started doing like classic voicemail and stuff. And they're like, no way. Because usually when you're like, I do voice work, you're thinking like a character from a show or a movie or something. It's like,
All right. One of my recording devices decided to be
that I saw?
Yeah, I just usually like to have the
Oh, I
one
keep forgetting that.
thing
I'm
ahead.
sorry. I knew that. They went to sleep, and I was like, I know there's one thing that I'm gonna miss.
No worries.
All right, get that shit up. Okay, good.
I woke up this morning, my hair was literally straight up, like Marge Simpson style.
Oh,
I was like, I'm kind of tempted to just do the recording like that, to see what the reaction is, but no, I'll be professional.
tell me we're out of shampoo. So it was like, well, I guess just conditioner. Yeah, I'm not doing that again. My hair was like, poof. Oakley dokley. Good there. I'm gonna take you off screen. Go back here. Start recording. White card, then we'll be good to go.
Don't record till you can see the whites of their eyes.
This semester's been so weird for me because usually we changed all the scheduling and kept the scheduling for when I was out on paternity leave.
Mhm.
So normally I have 3 full days in the studio, no question. I work from home one of those days, and then Fridays we try to keep open for get all caught up on editing. And this semester I'm not in this. I'm only in the studio when I'm picking up stuff. It's very weird.
Yeah, I hear
Almost like
that.
trying to get back in the swing of things has been fun.
Yeah. Just long enough to develop a new routine, so you can have to break that one. Yeah, I just assumed, but okay, cool.
You good? Stuff.
Yes. All right, cool. The teleprompter is still in sleep if you care.
It is.
It appears that way.
That's when I recycled it. It went off. Sorry about that.
No worries.
Like a remote button back there that apparently is not working. That's what I was
Yay!
Yes, I see it. I don't know what you're talking about. Because I'm the most important person. One of these things is not like the other. All right, here we go. Good to go.
Good to go.
5, 4, 3.
Hello. So, in this video, we are going to be talking about sort of the general sort of umbrella of mathematical reasoning. Sort of what is it, and give an example. So, mathematical reasoning, this is really the process of sort of converting information into the mathematical language so that we can then apply deductive logic and sort of figure out what we want. So, the sort of layman version of this, right, is the idea of going from like colloquial language to mathematical language so that we can then sort of mathematically or logically work through a problem to get to whatever answer we're after. So, by way of example, I figured I would actually give one that actually happened to me. So, my mother is a professional potter. She's an artist for many decades now, and she's building a wooden kiln. And wood kilns are very complicated things because wood does not sort of burn hot enough to actually be used in a kiln normally. So, there's all kinds of fluid dynamics and stuff involved. You'd think that's where I come in. Not so much. So, in one of my visits, my mother came to me to ask. She said, "Okay, we're laying the base of the kiln, and it has to be really exactly rectangular in order for the fluid dynamics and everything to work out." The problem is that she had a straight edge, she had a ruler, measuring tape. This thing is very, very large, like 12, 15 feet long. And yet she sort of didn't have a T-square because it broke at the time, and she couldn't go out to get one for various reasons. And she asked me if there's any way to determine if the sort of right angles really were right angles from just having a straight edge and a measuring tape. So that's sort of the colloquial version, right? She comes to me, and even though it has some math language mixed in there, like right angles, it's really just a problem. She's like, "Here's a problem. Can you solve this?" So I thought about it for a little bit, and I'm like, okay, jot down a thing. I want to know, here's this sort of rectangle we think, right? This rectangular structure we're trying to build. And we want to determine, okay, how do we know if the angles are sort of square, right? How do we know that they are actually 90 degrees without having some sort of right angle measuring tool? So I'm looking at this thing, right? I literally took out a piece of paper, jotted this stuff down, looked at it, and I was like, okay, I have these 4 angles. What do I do? Well, the sort of classic thing to do in geometry, take your rectangle and start looking at the angles by measuring the lengths, right? That's the information we have. And then cut that thing in half, right? Make this thing a bunch of triangles, because in practice, right, with really any shape, you sort of reduce it to triangles a lot of the time and see what you can do. But when I was looking at this, you're like, oh, okay, well, that's a right triangle, right? Or at least I hope it is, because the whole question is whether or not that thing is a 90-degree angle. But all I know are the sides. But we have a thing to relate these things, right? Specifically, our good friend, the Pythagorean theorem, right? That classic example of when would you ever use this? So the Pythagorean theorem says, okay, if you have a triangle, that triangle is a right triangle if and only if it sort of has that property, right? A squared plus b squared equals c squared. Usually we do that to figure out one of the side lengths, but we can go the other direction. We can say, okay, if a squared plus b squared equals c squared, that tells me then that it must have been a right triangle. So in particular, that angle, right, this sort of angle down here that we're not sure about, that thing is actually going to be a 90-degree angle, which is what we wanted, right? And in fact, that one measurement, right, that one diagonal C value gives me the bottom and the top, right? The bottom right, top left in this case, angles. I want all 4 angles, but if I go back to my original rectangle, I can just take the other diagonal and do the same thing, right? Check the bottom left and the top right. So this is exactly what I told my mother. I was like, okay, what are the lengths supposed to be? Use the Pythagorean theorem to calculate what the C length should be, right? What the diagonal is, and say, okay, well, it's a right triangle if when you measure sort of corner to corner diagonally, you get exactly this length. And if it's a right triangle, that means that you have a 90-degree angle. So just measure both diagonals, make sure that the right number, as well as the lengths, as long as everything's straight, you're good to go, okay? Now, this example is not intended to be like, see, we do use Pythagorean theorem, because what are the odds that you're going to like run into a kiln building problem in your own life, right? The point of this is that if I sort of just get the problem and I'm like, how could I do this? It's very easy to be like, I don't have enough information or I don't know. The idea is to be like, okay, translate it from the English thing, like I have this problem and I need to know whether or not these angles are 90 degrees, to, okay, how could I tell if it's 90 degrees? What things do I know about? Well, I know sort of a bunch of geometry, a bunch of trigonometry. Which of those things have to do with 90 degrees? Pythagorean theorem is like the go-to thing. Is there a way I could apply that somehow here, right? So it's more about sort of understanding that when you learn this material, it's not necessarily because you're going to use it this way, right? It's that you want to have it in the back of your mind so that when a problem comes up, you can sort of do this process of, okay, translate it into something sort of manageable, mathematical, sort of draw the picture as it were, so you can see what's going on and see if you can then sort of bring your tools to bear. What tools are sort of applicable here? What might get me where I want to go? That's the process of mathematical reasoning. Okay. So what we do? Well, we talked about mathematical reasoning sort of at a high level, this idea that, you sort of get these colloquial problems, these sort of just casual language problems, shall we say, that maybe don't have a lot of precision to them. And then you want to sort of filter that down to something precise that you can sort of write out, not necessarily as a formula, but, as a picture or something that you can sort of really get real information on. You can sort of very closely analyze each of the pieces and then see what tools you have that might work. And that process of sort of converting it to something that you can really work with and then working through it with whatever tools you have that are sort of available, that's what mathematical reasoning is. Okay, so that is that. Ba-ba-da-ba.
So the only thing with that is there was
The
not
pointer
a-
messed up.
Yeah.
Yeah. So is that really annoying to fix?
That is something I can't fix.
Okay.
Just because it records directly on the surface on the PowerPoint
Yeah.
when it does it, so I can't swap it out unless I come in here later and try to do it. But it might not be the exact same thing.
Right.
And with you being on screen for the whole thing,
But I have to do the whole thing over. Is it possible to just remove that sort of event entirely, meaning
Yes.
like just
Yes.
play as if it didn't do that?
Yep.
Okay. I think that's fine because there wasn't really a whole lot there.
where it was. Okay, I'll just make a note.
I think it was roughly around there because I tried to point out the right angle. I also have no idea how to actually fix that pointer aspect.
Oh, in terms of getting it to the
Yeah.
I got you. So with this one, it's fun. Double tap the top button, goes through. It's different. That's a magnifying glass, and now it's the red dot.
Okay.
So
Is the mouse supposed to show up like
here,
that?
like this one here. It shouldn't now.
Okay, cool.
It's fun things of, hey, you woke me up. I
Yeah.
can do stuff. I'll make a note for that. We'll remove it entirely, and then we'll have the red dot going forward.
Cool. Speaking of that, I don't know if this is still on your schedule or not. We had talked at some point, I guess, about 5.2.
Yep, we're not gonna do it. That's fine.
Yeah.
Yep.
Cool.
Let me know. It's like the module 5.2 has been like it's happened for like 4 different courses. Something has happened on 5.2.
It's bad juju. Just step away. Yeah, no worries. I gotta fix that too. I can fix that. That's text. Well, I'll try, and if I mess up, then I'll summon him.
Josh says if you want to just close it, he'll fix it. Unless you want to fix it.
I'll type,
Ooh,
and we'll
Josh is
see.
touching your slides. It's technically his slides. Always joke. I'm always like, I always feel like Home Alone. Macaulay Culkin's like, Buzz, I'm in your room. Mountain pound me.
All right, Josh, is that acceptable?
typing. Yes, but he has to fix the animation.
Okay.
So what I'll do, because
I will save and exit it, and he can.
I also have to get out of this one.
Yeah.
All right, Josh, we're out.
Is the teleprompter supposed to be saying no signal?
Nope.
I
What's going on?
mean, I know you said you closed it out, but that seems a little excessive.
All right, going home. Do the recording. All of a sudden, it's like, oh, bye. Okay, Josh said, let's go. Or let's figure out what's going on. Was it up there and then it just disappeared?
I wasn't actually looking, to be honest with you.
Well, I mean, it was there last
It was there
morning.
last time, yeah.
I didn't do anything. Great. Is it back up?
Nope.
This is definitely one of those days, you know, it's not really supposed to.
Oh, that's also got an error.
Any pop up?
Nope. Hey, Josh, if you're listening, that square root of -1 should just be -1, not square root of -1. I don't necessarily want to mess with that just because PowerPoint does bad things with equations. I'm a little sad I didn't catch that since that's actually my area of research. I'm a complex analyst. Having the I not be defined right is kind of sad. Are there any like switches or anything it goes through on the way to the computer?
No, it's just a direct USB, or not USB, but HDMI.
Huh. And I assume the computer is rendering it fine on the
I'm
other
seeing
side.
everything back there. It's not showing me anything any different. It's literally just the output here.
Hmm.
Which is quite annoying. Back.
Thanks, Josh. I love this graphic, by the way, Josh. Did great. Cool. I mean, I can sort of just roll without one. I mean, it's not that huge a deal, but I imagine that is something you're going to want to figure out.
Teleprompter is dying.
Yeah.
Can we take 5 more minutes? I'm gonna go get Army to help 2 people. Wiggled hello. It's going from that.
Oh, no, I thought it was very Christian.
It's going from the display port. Yeah. To HDMI connection. And the HDMI all the way to it. So we did
That monitor, right?
Yeah. Did fine. We recorded the first one, saw everything. Everything was good, and now it's no
Not
signal.
coming up into here.
Maybe a stupid question, but did you make sure that Windows is actually duplicating the monitor feed?
That's a good question. I will check. Which one's the teleprompter? This one? Yes, yes, yes. Should have just switched out of duplication.
I find Windows does a lot of stuff it shouldn't
Yeah,
logically
the way it
do.
dropped out made me seem like the cable was dying.
Yeah. Hey,
It's back.
I see a Windows backdrop now.
So is it doing that stupid thing?
Well, let me wait. Don't extend yet. Let me duplicate it.
Yeah, that's what I'm saying. 'Cause remember this went through this stupid thing where we duplicated it and then it wouldn't work?
It's
Now
got a
it's doing
signal
it
at least.
back to free now.
Yeah. He figured it out.
I didn't even think that was it because the way it just died.
Yeah.
I was
I don't know
thinking
what-
cable went bad.
I don't know what would kick it out of there.
Yeah, I didn't, literally was doing PowerPoint stuff, was not in that. And if there's a hotkey, I found it somehow.
Fascinating.
All right, well, thank you for your help, Ami.
All you needed was Jason.
Good to see you, Ami.
Good to see you, too. Well, that was fun. All right. All right. Sorry about that.
No worries.
I hate that stuff that it could be like 16 things and I'm up to like 14 and it ends up being like
Yeah.
the easiest thing.
Many, many moons ago in another lifetime, I used to do
Yes.
tech support.
Yep. Is your computer turned on? Yes.
Yeah.
Have you fed and watered it recently? Oh, whoops. All right. What I did last time.
Well, I'm gonna start recording before anything else decides to go. Go back one real quick. There we go. White card.
That's the one fun thing is just when a computer goes bad, there's rarely few things like the computer went bad or there's a ton of things it could be. With this, it's like, all right, the 18 cables going from it's like the camera works, the
Yeah.
cable works. It's like we have a diagram of every piece of cable that's in here for that
Yep.
very reason.
That's why one of the first questions I asked was, are there any connectors between? Because it's like, that's always the stuff that I forget is to be like, okay, I've checked all the end
Or
points
is
of the
there an
cable,
HDMI
but
to SDI converter that died, or
exactly.
fun stuff.
Yep.
All right, sir, good to go.
Good to go.
And 5, 4, 3.
Hello. So this video, we are going to be covering or perhaps reviewing the various types of numbers. So first up on our tour of numbers are the natural numbers. So natural numbers are whole numbers. So particularly they have no sort of necessary fractions or decimal points, but these things are strictly positive. I'm going to put an asterisk there because it turns out, depending on who you ask, some people like to include 0, some people don't include 0. So the most popular one is the 1, 2, 3, 4, 5, 6, etc., not including 0. But again, if there's sort of any question, it's always a good idea to ask whoever's teaching your class or whatever, situation you're in, whether or not they're counting 0. And as a forewarning, they will probably say something to the effect of course we count 0. That's what natural numbers are. Or, of course we don't count zeros. That's what natural numbers are. So just know that there's strong beliefs about that particular part. I also want to point out here a sort of subtle but important difference about this thing, which is that we say no necessary fractions or decimal point, meaning that if we write something like 4/1, that is a fraction, like it has a fraction form, but that would still be considered a natural number because it's still the number 4. It just is in a different format, right? So this sort of little thing to notice here is like if you can reduce it or sort of rewrite it into a way that is a natural number or whatever type of number, then that's what it is, as opposed to sort of messing with the format to make it look like something else. All right, moving on. So next up, we have integers. So integers are basically the same idea as the natural numbers, but now we're actually allowing the negative and 0 as well. So we're going to have, the 1, 2, 3, 4, but we also have the negative 1, 2, 3, 4, as well as 0, but still whole numbers. Next up, rational numbers. So rational numbers are sort of these fraction things, but specifically they're fractions where the numerator and the denominator, these are both integers, right? So they aren't just fractions, it's fractions where we actually have sort of the ratio, which is why we say rational, but it's the ratio of these nice whole numbers, positive or negative. Now, in practice, these actually can have a variety of forms because of how we happen to write numbers. So rational numbers, we define them as these sort of P over Q things, where P and Q are both integers, but they also sort of, the other format they have, which is just as legitimate, are these sort of decimal forms where they have either finitely many decimal points, so it sort of goes for a little while and then stops, or it can have infinitely many digits as long as it sort of has a repeated pattern. So as an example, we could have something like this, 3.1415926 thing. And since I stop at 6, then that means I have finitely many, right? I only have however many that is, so like 7 or whatever decimal points, and that's a rational number. And it's a rational number because if I sort of write a appropriate power of 10, it'll move that decimal point over, and so I can write it as this sort of ratio of integers. So it's not just like we're defining it to be rational. It is legitimately rational. I can write it as that fraction. Notice I don't have to necessarily write this in lowest form to show, right? As long as it's writable in some fraction, I'm good. I don't have to make it sort of the right fraction, as long as it's equal. The slightly trickier version is that that sort of infinite number of decimal points, but with a repeating pattern. So for example, we could have something like this, 2.34 and then 1, 2 repeating, right? That's what the bar over it means. Now, there's actually a trick to show how you actually get this thing to be a rational number. I'm going to go through it just because you should always have seen this at least once somewhere. But this is not a thing that we're going to be asking you to sort of do in practice because it's sort of a trick you can look up and you rarely actually need it. So the process to make this a rational number, we're going to take that thing and call it something. We'll call it X, but I could call it balloon if I really wanted to. It's whatever. I just need a thing to keep track. Then I'm going to multiply this thing by a power of 10, where that power is how many repeating decimals there are. So since it's 1, 2 repeating, two numbers, I'm going to multiply both sides here by 10 to the second power, which is 100, right? So on one side, my X times 100 is just 100X. On the other side, I'm moving that decimal place over 2 points, which happens to coincide to this 234.12 repeating. Now, I can sort of write that 1, 2 as many times as I want. That's what it means to be repeating. I'm going to write it one more time for a reason of clarity. I don't have to, but that's why I have this 0.1212 repeating, is that I'm going to do something in a second here. And the thing I'm going to do is subtract off that original X. So here I'm just subtracting X, but over here I'm going to subtract what X is, specifically that 2.3412 repeating. And the idea is that that 1, 2 repeating part in both places overlap perfectly, so they cancel each other out, and I'm good. So what's left over is just that 234.12 minus the 2.34. So I have that 232.78, and that is equal to the 100x minus x, which is that 99x. All right, so now I can isolate x, divide both sides by 99, and then this looks really awful. I don't like having decimals and fractions together, so I can multiply the top and bottom by 100. And finally, I am at this thing where I have this sort of nice integer on the top, integer on the bottom. That means I have a ratio of integers, so it's a rational number. And if you actually sort of did that division out, you get back to that 2.3412 repeating. All right, so that's a little trick to show / prove, not really prove because it was an example, but prove using that line sort of loosely that these sort of repeating decimal digit decimals are also rational numbers. All right. Next up, real numbers. Now, this is going to be the most hand-wavy of definitions you're going to get. So real numbers are any number that you sort of deal with normally. I'm saying that because it turns out the actual mathematical definition of the set of real numbers is surprisingly deep and complicated and takes a couple plus years of sort of math major courses to understand. So we don't want to go that way. There's some deep magic happening in the background. But really all you need to know is that real numbers are sort of all of those numbers we've been thinking about. So it includes all the stuff we've already discussed, as well as things like square roots and pi and, you know, those things that aren't rational numbers that don't have those sort of nice repeating decimals. So by way of example, right, we can have negative whole numbers, you know, our integer type things. So -3, -2, -1, 0's in there, square root of 2 is in there, square root of 3 would be in there, that 3141596 over 10 to the 7th, that thing's in there, right? Like all the sort of typical numbers are in there. Now there is one that's sort of a little bit bigger, which you may or may not have heard of, and we will sort of talk about in this class, and that is the complex numbers. We're going to get there in a second. I do sort of want to, before we get there, mention, because I did technically mention this, the irrational numbers, those other numbers. So rational numbers, those are the real numbers that we haven't talked about, the real numbers that are not rational. So those are the things that have the infinite many decimal digits, but no repeating pattern. So square roots, or really any roots that don't sort of simplify nicely. So that's an example. Pi, another example, right? It goes on forever and doesn't really repeat. E, another example. So there's sort of these other numbers that aren't, right? We've been looking at sort of building up the whole way, right? We had natural numbers, then integers were like a bigger thing, and then rationals were a bigger thing, and then reals were a bigger thing. But there's sort of this irrational numbers that's sort of off to the side. And we'll have a nice little diagram for that. But going back to our real numbers, we can go yet bigger, right? So these are the complex numbers that I mentioned. And these are sort of numbers that include some multiple of that imaginary constant I, where we sort of define I in this weird way because we want something squared that is negative, really in particular -1. So I squared being -1, that's how we sort of create these complex numbers. All right. So there's a lot of different types of numbers, and they're sort of related in a very sort of straightforward way, but it's hard to tell just from their definition. So by way of sort of demonstration, there's nice, I hesitate to say Venn diagram because there's not a lot of, there's a lot of concentric pieces in this. So we start with sort of the biggest group that we talked about, the complex numbers. Complex numbers are sort of all these different numbers, a subset of those, sort of a smaller piece of things that are all complex, but sort of have their own thing. That's the real numbers, right? So all real numbers are also complex numbers, but not all complex numbers are real numbers. Then the real numbers split into two pieces that are sort of not, there's no overlap between them. That's what I was trying to mention earlier, where we have these sort of rational versus irrational, right? So we were sort of building up, and I wanted to make a sort of very clear note that we have this sort of irrational number set that's sort of separated off to the side somehow. So that's how we split up our real numbers. Then in our rational numbers, inside the real numbers, we have integers. So again, all integers are rational, but not all rational numbers are integers. Then within integers, we have the natural numbers. So again, natural numbers are integers, not all integers are natural numbers. Okay, so this is our sort of nice little infographic piece that has sort of how these things are all interrelated. Okay, so what did we do? Well, we talked about the types of numbers. So we started out with the sort of smallest in some sense set here, which is the natural numbers. Then we went up, right, a grouping to go to our integers, which are sort of the natural numbers, all those positive whole numbers, but now the integers include the negatives and 0. Then rationals, so we can talk about, fractions of integers. Then we had that split, right? So we had the rationals, but then we had the irrationals, which are sort of unrelated, although they are related, right? Because they're sort of the not rational real numbers. But then we had the real numbers, which is sort of all the rationals and all the irrationals. And then finally, the biggest one, we had our complex numbers, which if you haven't heard of, if I doesn't ring a bell, don't worry about it. We're going to sort of dive into that one later on. Okay. So that is that. Whoa. So far, it looks like it still exists.
Yep. Got 1, 3. Go.
I am good to go. Crunch, crack, crunkle.
Yeah, I do believe myself. My kid played video games for the first time like yesterday.
Oh.
He's always messing with my controller.
Mhm.
So I was like, you know what? I'll let you try it. So I downloaded like Paw Patrol
Mhm.
Racers, which is pretty good for what it is. It kind of reminds me of Mario Kart.
Ah, nice.
Without, the theming, obviously. But they're still like, I don't know, throwing pies at each other and whatnot.
Nice.
I thought he was really good until I realized the easy mode just kind of steered for you, so he wasn't really doing anything.
They know their market.
So I was like, oh, it's okay. He enjoyed it, which is all that mattered.
Yeah.
All right, here we go.
Good to go.
5, 4, 3.
Hello. So this video, we are going to be talking about sort of mathematical reasoning, and in particular, this idea about mathematics as a language. So in reality, mathematics really is its sort of own type of language, and that's sort of confusing because, it's not like we have radically different sort of vocabulary per se, so much as we sort of reassign what words mean. So that can be sort of very difficult to understand at first glance. A good sort of introduction to this process, though, is what seems like a pretty simple, straightforward question. How much does water weigh? Right? So if I ask, 100 people this question, I might get all kinds of answers back, right? And the thing is that those answers, sort of no matter what they are almost certainly not correct, not because what they tell me is incorrect. Maybe they have perfectly factually accurate statements, but because this question is sort of too vague to actually do anything with. And this sort of gets to the heart of why math has its own language or its own sort of way of using language, is because mathematics, we have to be really precise before we can really do much of anything, right? Like if this were a question on a math test, how would you even begin to think about this, right? But the reality is like this is a mathematical question, just not in a mathematical language setting. And that's sort of the process of mathematical reasoning that's difficult, is going from this question to something you can use. So by way of sort of example, hopefully you've thought about this a little bit and maybe got an answer yourself. I say, okay, how much does water weigh? Well, how much water, right? So if I ask 100 people how much does water weigh, and they give me a bunch of numbers or answers or whatever, and then I ask people, okay, what were you thinking about as water, right? As a type of water or quantity of water. Some people might be like, oh, I was thinking like a milk jug, right? Or a glass of water, or a lake, or the ocean, or all water in the universe. Obviously, the answer you get is going to be radically different, not because, they're necessarily wrong, although coming up with a number for all water in the universe would be impressive if you were correct. But nonetheless, not because the answer was wrong so much as we didn't have the same understanding of the question, right? And what's worse is like, okay, what if we said it was a glass? Everybody came back, right? All 100 people were like, oh no, I was definitely thinking of a glass of water. Well, okay, fair enough. But how big is the glass, right? Are we talking a 16-ounce glass? Are we talking an 8-ounce glass? Are we talking a shot glass? Are we talking, like a stein or something, like a beer stein, right? Like a glass, again, is not actually specific enough. It's not precise enough. Moreover, how full is the glass, right? I want to know how much the water weighs, not how much the glass weighs. Is it half full, 3/4 full, empty, right? Then the water weighs nothing. Hooray, right? So again, even if I knew it was a glass, and even if I said it was a 16-ounce glass, still not precise enough, right? Finally, what kind of water, right? Like water does have different forms. Is it ice? That would have a different density and thus weigh a different amount. Is it liquid? It's probably what people were mostly thinking of, because we usually think of water in its liquid form, but it could be steam for all we know, right? So again, in order to sort of get at this thing, we need to be much more precise about what we might be asking. And we can go down this rabbit hole all day. So I'm going to sort of, hopefully I've made my point. I'm going to stop here. But this is the process, is going from how much does water weigh, right? That might be what somebody asks you. And you have to sort of flip it back and ask them a bunch of questions and be like, okay, what you really want to know is how much does 1 liter of, say, liquid, right, room temperature water weigh? That's what you really wanted to know. You just didn't actually sort of say that when you said how much does water weigh, right? And this can be why it can be very frustrating to talk to math people sometimes, because you might ask a question that seems obvious to you, and all you get back is 1,000 more questions. And it's not because they're trying to be difficult. It's because this is sort of how the math process works, is we have to take what you think is a specific question and make it really precise enough that then the math person can actually do something with that piece of information, okay? So mathematical reasoning, this whole idea of like applying logic, formulas, variables, all of these things, this really only works with very specific kinds of information. In particular, very specific sort of precise information. I need to know like 1 liter, not just water, right? I need to know that it's liquid or solid or vapor or whatever. And as a result of that, translating that sort of colloquial language, right, going from how much does water weigh to I really want to know how much 1 liter of room temperature liquid water weighs, that's usually the hardest part. Like that's usually where a lot of the effort comes in. So we're sort of going to be spending a little bit of time of trying to figure out how to do that process to go from sort of a typical colloquial question, something that somebody might actually ask you in day-to-day conversation, to how do you actually make that into something that you could actually use a mathematical tool on if that's sort of the appropriate tool to use. Okay. All right. So what do we do? Well, we talked about this idea of mathematical reasoning, and in particular, the sort of language or linguistic aspect, the fact that really mathematical reasoning only works on this really sort of precisely stated information, that you need a lot of precision in order to actually even begin to use tools. You need to quantify stuff, you need to qualify stuff. And so a lot of this sort of process of using math in the real world or trying to model something mathematically, a lot of that is actually just doing that translation, just going from you said this thing, what you meant was this other thing that seems ridiculously sort of technical how I've rephrased it. But now that I've done that, I can actually start doing things like assigning variables and plugging into formulas and sort of deducing what the answer that you're after is now that I know precisely what it is you're after. Okay. So that is that. Da, 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 da.
You hear, it's just kind of part of my childhood when I went to go to school. But Jerry Springer died today.
Really?
Yeah.
He had an MBA from Harvard.
Yep.
Trying-
Doing the show though.
He did.
And then he was a big entrepreneur after that. I did hear he was actually quite a bit of. Did you load up 1.4?
1.5.
Okay, good. I loaded up 1.4.
He's also the mayor of somewhere, right?
Yeah, yeah. I don't remember.
Hey, Josh, do you think that square around the 2 being green might be misleading? I mean, it doesn't show up until the constant bit, but I don't know what other color we could make it.
Like when I look at that just from the C2 and the C, I feel like it's related because it's the same color.
That's what I was thinking too.
He's typing. He said, what should it correspond to, or is it just highlighting the 2?
So the constants box and that 2 should be linked together without it being linked to the other stuff. So like we could change the purple and the green, the purple of the box and the green drawn box to a different color if there's even another one to use.
So just bring attention to the square to the W, but that's
Yeah.
purple because it's a constant.
Right.
Gotcha. Smart people. Typing. I mean, in that case, I would almost use like red or just a color that didn't coincide to any of those colors.
That's what I was thinking, but then with the colorblind
Uh,
palette thing, I don't know how that really works. That's firmly outside my area of expertise. Should I close this? Is that
he's just gonna come in.
okay?
He'll just do it on the fly. It's just some things are just harder to communicate because there's not a
Yeah.
voice communication. Yeah, Josh, just come on in. And also, it's weird too because he's messaging me on Teams.
Hmm.
I got one on the computer Teams and not on my phone, and the other one I got on my phone and not on the computer Teams. So I think I'm just gonna do pen and paper today because nothing seems to want to work for me. So
Yeah, you're not having the best of luck with technology.
I should have messed with my Xbox tonight.
Sorry. I
So
was
did you
confused.
understand what I was talking about?
Mm-mm.
Okay, so this purple box is supposed to correspond to that 2, but I'm noticing that we have a green box around
Oh,
the
I
2,
see.
which corresponds to the C. So I'm wondering,
We were thinking about using like a red or a white. That works.
yeah, I'm wondering if it, because like we could use a purple, but then the W is also purple, which is not a constant. So I'm wondering if it would even make more sense to make the 2 and or the box and or the text box thing like an entirely different color than purple, or the W a different color.
So I
Might be
will say
easier.
The white box around the 2 makes it look like it's a part of the.
Thing.
Yeah. What
So
about red? Red's usually a call out.
so the purple things up here aren't constants.
The 2 is, but the W is not.
So should this just be white?
That's sort of what I was
Yeah,
thinking. Is we can make the
white.
W a different color entirely.
Now, is that the same for the D2 or is the D2, C2, are they both constants?
The 2 in D2 is not an independent variable, so you can make the 2 a different color. You could even make it a purple color to match the other 2. Same with the C thing. And then, yeah, that one.
So just a dumb question here. So people are gonna be like, oh, there's an orange, there's a green, there's a purple, there's no white.
I
There's no
think-
white.
I think a lot of this came from the previous slide where we did
Oh, shoot.
that, which like there's no reason that the 2s have to be any coloring here, because really the important part is that it matches those letters, which are just letters. So like you can just do the white as white. Yeah.
Drew the white default text, so
Yeah.
I
Which
think
is how I
it's-
use in my notes and stuff as well. So
I think it's okay.
I'm hoping that's clear.
So but this
But now the W doesn't match the previous slide, if that is a thing. Because we do want some way of noting. I mean, white could be the color as long as it matches that thing.
too many variables. Let's just, can we do it there and then no? Okay, I'm just gonna make this a different color.
I was going to ask if there's sort of a natural or a colorblind safe color to use.
Let's do this one.
Do we care that we're matching the edges?
Dadgummit. There's too many colors.
Yep.
That's the same thing as that. Red it is.
Which gets that, yeah, box then background needs to be.
Okay, so then this box needs to be purple.
But now we can make the W's red,
Oh,
and now everything sort of matches, I think.
okay.
Does that make sense?
Yes, but just the W's don't correspond to anything on here. That
Which is fine. Yeah.
Okay, so that's fine.
Of course, I say that, but it occurs to me that the whole reason it doesn't correspond is because W is also an independent variable as listed here. So now that we've done all that work, it actually might make more sense to make W orange with the other one.
Okay. Same here.
Yeah, I think so.
Okay, so this.
And in fact, yeah, I can make that a teachable moment at the same time. So I'm good with that.
And this will be orange too?
Yep.
Okay. Your funeral.
Just kidding.
All good?
Yeah, I think so.
Okay.
See, I know you're just cooped up in your office all the time, so I just gotta, make things difficult so you come down here. Thanks, Josh. Cool. All right.
So the only thing that'll be a tad bit different since you changed it, I had the secondary open on the teleprompter. So it'll just be different colors. It'll be the same clicks and everything.
Yeah, you're good.
If that's gonna bother you, I can close out and reopen.
I don't care.
Okay. Straight through the record. It's fine. All right, cool. Start recording.
Yep.
You got this semester's almost done.
Well, that means finals are almost here, which means my students are going to start bombarding me with emails about how they just need 27 more points at a 200 or whatever.
Yeah.
Like, I'm only a full letter grade from passing. It's like, oh God, you're killing me.
Where is your class located?
Online. Yeah, exactly.
What
I've had that. I've had students email me, be like, I went to your office and you weren't there for office hours. I'm going to complain. It's like, under office hours, it has a Zoom link. I don't even did you look up my office to find it?
California for Alrighty. Here we go.
Good, you
And 5, 4, 3.
Hello. So this video, we are going to be tackling variables, and in particular, the sort of different types of what I will say is variables, meaning that sort of the different types of things you would see in equations and formulas and stuff like that. So starting out, sort of a reference point, right? If we have like a square object or whatever, right? We have something that has these right angles, cut it apart. We have this sort of nice diagonal giving us our wonderful triangle, right? Pythagorean theorem. So we might wonder something about, say, the distance between the corners diagonally. You can write out the Pythagorean theorem, right, where I've labeled these sides and the diagonal all as these letters. Pythagorean theorem gives us that, in this case, d squared plus w squared equals c squared, right, where I have the sort of depth and width and some sort of diagonal thing. And then I can solve for the diagonal, right, the piece that I want. So c is the square root of that d squared plus w squared. And in fact, you might actually recognize this almost as a distance formula, because distance formula is really just the Pythagorean theorem in disguise. But this is sort of an alphabet soup, right? We have all these different letters, and the thing is that they sort of mean different things. So it's useful to know what sort of role each of these things is sort of bringing to the table. So D here, D is one of the side lengths, W, another side length, and sort of looking ahead, right, foreshadowing, I'm making these things the same color for a reason, which we'll see in a second. C, well, that's what we're trying to get, right? That's the thing we're computing. And so that's sort of what the diagonal should be measured, right? That's what we hope the diagonal equals. All right. But our question here, right, about variables, well, going back to the variables themselves, if we look at sort of our nice little equation here, right, C, W, and D, the D and the W, right, these are independent variables, meaning that they're the inputs. They're the things that we can actually sort of put in as the things that we measure or supply as the actual sort of information, right? So if we're looking at a square or a rectangle, we can measure each of these sides and then put them into the equation to calculate C. So since we're putting them in, their input, that's why these things are the independent variables. And it's worth noting here that even though we sort of almost always, at least at this level, talk about sort of one variable inputs, right? We usually have some function of a singular letter, right? F of X or G of A or whatever letters we're using. There's no reason that you actually need to have only one, right? There's a whole sort of bunch of math where you have a bunch of different inputs. It's not a thing that we're going to be doing much in this class with, other than sort of talking about how they exist and roughly how they work. But that is something that if you're going far enough in math will show up a lot, okay? Now C, this is going to be our dependent variable. So dependent variable, that's the output. It's the thing that we're sort of calculating in our model. It's the thing that we're trying to figure out, right? So since the diagonal is the piece that we actually want to know about, That is the thing that is the dependent variable, so named because it depends on the independent variables. They are independent of the calculation, right? They're sort of whatever they are, whatever you measured them to be, and then you put them in, turn the crank until you get the output. The output is the dependent variable. Now, last but not least, there is another thing floating around here, which are the constants, right? So constants are just numeric values that sort of never change with the different sort of input values. So in particular here, the 2, right, the squared part of it, this is from the Pythagorean theorem, and it's not going to change. It doesn't matter if W is different or if D is different, right? Those things are still a 2. We're still squaring them, right? Whereas if I change D and W, then obviously D and W will change, and C may change as well, right? Because it depends on the other 2. So this is where you sort of get the difference between a variable, something that varies, versus constant, something that doesn't. Now there is a gray area, shockingly enough, and these are things called arbitrary constants. We're not going to deal much with those in this class. They do come up in calculus, in particular calculus 1. So we'll talk about them a little bit in this class, but they're not going to show up very much. Just know that they are a thing, and they're sort of a weird gray area between something that varies and something that doesn't. Which seems like that should be binary. Turns out not so much. All right. So what do? Well, we talked about variables and sort of variables in this loose sense, right? Like the things that you would encounter in some sort of formula where you have the sort of legitimate variables, things that vary. In that case, we have the independent variables, the stuff that we put in that are independent of the calculation. They're part of the sort of input process. And then we have the dependent variables, things that depend on the independent variables. They depend on the calculation. They're the sort of output or what we're after. And finally, we talked about sort of the easiest of the bunch, the constants, right? These constants are things that sort of don't change. They're the same number, the same value, no matter what sort of input you decide to put in, no matter what kind of output you get out, these things never change, right? And usually we just write them as straight up numbers, not letters, because they don't change. There's no reason to sort of represent them abstractly because they are what they are. Okay, so that is that.
Yeah, eggs out of this one, make sure to save.
Done. Good tip. So 8-2, yeah.
Yep. 8-2 and then 8-3. Just so I can verify, obviously you're on screen for the welcome, and then when you start the problem, are you on screen up until the stuff starts filling on the right side?
Sure.
I didn't know what your intention was on those. So.
I mean, that's sort of what I expected, but to be honest, I don't really have a strong feeling or opinion.
I say let's do it, because then you're going to be off screen for a very long time until the wrap up. So
Yep.
I think that works.
Okay. Nope, didn't work. Go back, I say back. Yeah, thank you. There we go.
Ear surgery.
Okay.
All right, I'm gonna start recording. Yeah, I like
finally beat Assassin's Creed Odyssey. It took me forever.
Nice.
And now I'm starting on Origins, and I think that might be a dumb idea. The new Diablo comes out in June.
Yeah.
And so I'm waiting because my buddy Brian, he used to work here, and his girlfriend Kelly used to work here. We all play that together, which is really
Nice.
cool. I've always wanted to play it, but I never. Growing up, my computers were always so crap. I could never play like games.
Yeah.
It's like I'd go and rush and get a game, and I was like, "You know, lowest settings."
Yeah, that one really doesn't work with lag either. That's a bad time.
Yeah, it's just kind of like, all right, choose your own adventure games.
Yeah. Text-based.
Yes,
Zork for the win.
like the original Dungeons and Dragons. Fantastic. All right, good to go.
Good to go.
Here we go. 5, 4, 3.
Hello. So this video, we are tackling synthetic division. So we've talked about polynomial long division, and now we're going to do synthetic division. So by way of sort of introduction, because these things are very similar tools, we're going to start by doing the actual long division version so that we can see the sort of parallel and why you might use synthetic rather than polynomial long division in sort of certain circumstances. So recall, right, looking at this here, we have this x minus 1, right, dividing into this ginormous polynomial. So we do sort of the same thing we usually do, right? We take the first term and divide it by the first term of the thing we're dividing by, get x to the fourth, multiply that against what we're dividing by, subtract off, right? And we keep going doing this, right? We drop the next term, do that same division. Okay, we're going to do x cubed, multiply x cubed against it, subtract off. Now we have 4x cubed, drop the next piece, et cetera, right? So as we're working through this, I'm going to make this sort of observation, and this was sort of an important deal that we talked about, right? Was this how we had to have all the terms here, right? So even though this was x to the fifth plus 3x cubed, we actually had to inject this 0x to the fourth and this 0x as placeholders. Otherwise, this whole process sort of starts to break down. So even though we're dropping 0x, well, we still need that so that when we do the 6x times our sort of divisor here, we end up getting something that actually lines up when we do this subtraction down here, right? But the flip side of that I'm going to notice is that as we're doing this, right, drop the negative 13, do that same division, it turns out sort of necessarily that I end up having all of the powers represented up here as well, right? So there's no sort of missing powers. And in fact, even if for some reason I couldn't divide it straight in, that means that I'd end up with like a 0x squared or something along the way. And so what I would end up doing is putting a 0 up top, right? So I would still have everything represented even if it had a 0 coefficient in order to make this whole process work. Now, if it doesn't go in evenly, I'm going to get a remainder, right? Here we have this remainder here. But then that means that we take that remainder and we put it as the sort of remainder bit on the end down here at the sort of end of the thing divided by the actual sort of divisor piece, okay? Okay, so why sort of go through all this? Well, it turns out that there's sort of a shorthand version of this process where we do basically the same thing, but instead of doing it with the x's and the powers of x's sort of having this tracked the whole way, we can do it instead without all those x's and their powers sort of put in together. And it turns out to take up a lot less space and be arguably a lot quicker. To that end, the first thing we have to do is actually take this thing and find its 0. And this is actually kind of an important, albeit subtle difference, because a lot of the times the 0 may not link up exactly the way you expect. We're going to see an example of that probably in another video, but as a first step, first thing we're going to do, set this thing equal to 0, solve. So we get x equals 1. Now we're going to draw a little grid piece where I'm going to take that 0 and put it in the top left corner. So that 1 over here where I got x equals 1 is indeed the one that we have down here. Now, the whole idea is to represent the powers of x's without having to write the powers of the x for all of them. So what I'm going to do sort of by way of showing in this video is I'm going to write out the power of x's, but this part you don't have to do. I will say that it can be very helpful to make sure you don't make a mistake. But I'm going to write out along this top little benchmark here, this top little segment here, all of our powers of x sort of just written out. So I have x to the fifth, x to the fourth, third, second, x to the first, and a constant term. And to be clear, I'm picking x to the fifth here because of x to the fifth over here, right? So I'm getting ready to sort of represent this polynomial over here via this stuff down here, okay? All right. So the way I'm going to do that is underneath each of these x powers, like here, I'm going to write the actual number, the coefficient for that power. So here I have a 1 here because it was the 1 over here. Likewise, for x to the fourth, I have a 0x to the fourth, so I'm going to make that thing a 0. For x cubed, on my left, I have 3x cubed, so I have the 3 over here. And this is how I'm going to get all of these pieces, right? So I have a 2, then I'm going to have that 0 from the 0x, and then I'm going to have that minus 13 for the c. Be careful that we want to keep the sign, right? Like all the other ones were positive, but I have a negative 13, so I have to make sure that I have that negative. Now, the next thing I'm going to do, again, I don't have to write in the columns, but it can be helpful to organize your work. At least think of it in terms of columns. And then I'm going to leave a little space down here below each of these numbers. And then I'm going to write another one of these sort of horizontal lines here to separate some stuff. So the first thing I'm going to do is drop that first number. So that 1, I'm going to drop that as a 1. Then I'm going to multiply that by my 0. So I'm multiplying by 1, but that 1 down here is this one up here. So if my 0 were 5, I would multiply by 5. If it were negative 17, I would multiply by negative 17. Once I've done that, I'm going to rewrite it below the next number. So I multiply by 1 to get positive 1, rewrite that below the 0, and then add straight down, okay? And repeat. So now I have a 1 on the bottom, multiply by that 0 again, the 0 being this red 1, right? So I have a 1 here, so I'm going to multiply by 1, which will get me 1 again, write that underneath the 3, add straight down. Take that 4, multiply it by that 1, because the 1 is the 0, that gets me 4, put it underneath the 2, add straight down, rinse, repeat, right? So I'm going to keep going until I get my negative 7. All right. Now I have effectively sort of completed the process, although it doesn't necessarily look like it. So looking at this, right, getting rid of the little instruction there, what I've managed to do is pull out, as it turns out, the coefficients for my new sort of function, where each of these columns, I'm going to write one smaller of a power. So here I have x to the fifth, so underneath I'm going to do x to the fourth. So that 1 corresponds to 1x to the fourth. The next one, 1x to the third, 4x squared, 6x, 6, and then that negative 7 is actually a remainder, right? Negative 7 over x minus 1. And then if I look at this thing here that I've now sort of computed is exactly the thing up here that I also computed, right? So I can actually rewrite this as the same format where, again, I'm recognizing, right, that this 1 that I'm sort of corresponding to, right, the 1 that I got down here, this corresponds to this x minus 1. So I'm going to rewrite this as x minus 1 times, and then my function down here, okay? All right, so what do we do? Well, we sort of went through an example and talked about synthetic division. So in particular, synthetic division is sort of the same idea as polynomial long division, but without any of the x's or power of x's. This can be nice because it can be way faster, right? If we actually sort of went through that quickly instead of going very sort of slowly to make sure everybody was following along. But if we went through it quickly, I mean, there's very little in terms of complicated calculation, and it's sort of just those lines, you know, a couple lines of numbers. So you can go through it very fast. But there's some drawbacks too. So we're going to look at those a little more closely in the other videos. But in particular, these things only work for linear things. So in particular, like I needed a 0 that I could plug in. So that makes it so I can't really divide by something like x squared plus 1, because x squared plus 1 doesn't really have a real value 0. So synthetic division doesn't really work. So synthetic division really only works with things that have the sort of form x plus a number or X minus a number, things like that. There's some other caveats too. For example, it's harder to see when you make a mistake because you don't see the powers not matching up. If you forgot to put in a 0 somewhere, for example, everything will look like it works, even though it's not. So there are some drawbacks, but if you get used to it and you're sort of using it correctly, it can be very quick in comparison to long division. So it is a very useful tool. Okay, so that is that. So I went through this and then it looks, something's bothering me about this. I think there might be an error.
Okay. You've got my attention.
Because that really looks like that should be minus, and then that would become a plus, which means that bottom number really should be 19. But over here, I'm getting -7, which makes me think that things have gone badly somewhere.
I blame Josh.
I mean, I'm good with that. We can do that. I'm okay.
I'll just blame it on me. It's fine.
I'm just looking through here for a minute. Ah, there's the problem. Whew, I feel better now. So, Josh, this should be a -13, not a +13. And then everything works.
Drop down.
Yep.
So I don't think you said positive 13.
I'm pretty sure I didn't because I saw that that didn't look right, and I was like, don't say anything about it. Don't say anything about it and try not to use the pointer on it. Which I maybe did anyway, but I also tried to make it so that wouldn't matter.
All right. So basically slides 3 through 11.
But the good news is that means the other side was correct, which means I don't have to redo anything there. That was my concern.
Said he'll fix it when you close the PowerPoint.
Okay.
And then I'll make a note for the editor to insert new PowerPoints.
Okay. Yeah, that should be good.
All right. Stop. Did you already pull up 8.3?
Yep. Hey, Josh, these green box versus blue box, they should technically animate in the other order, meaning like the green one should be first, then the blue. Is that doable? I should quit out so we can do that, I guess.
Blue, then green, correct? Opposite of what was there?
The opposite of what was there, yeah. Yep, perfect. Thanks, Josh.
get you out just in time before the rain hits.
It's optimistic. Frankly, would not correspond to my luck very well.
Well, maybe the computer will squirt water out at me, so it'll be fine. That would be my luck.
That would be how things are going.
My Muppet comes up from me on the table. That's like we're dealing with our construction still hasn't started yet on our house, and we've had some damage to our vinyl siding, which I haven't fixed because we're going to get it completely removed from the construction.
No, yeah.
And now we had a family of mice move in.
Of
So,
course.
I trapped my sixth one today.
Oh,
Then had to go release it. My son's like, I want to pet it. I was like, no.
not so great with wild animals.
Yeah.
So Josh, this division thing here, this one should be in line with the top line, if that's possible. And there were some other ones of this form too earlier. Here with the 3 halves and here with the 5. I think that's all, but let me scan. Yeah, that's all of them.
He said, okay, fixed. Sure, anything, so
He's not the only wizard.
y'all just way too ahead of me at this point.
Cool. Okay. Cool.
And white. Start record. I know they kind of brought back the Muppets, so like I kind of wanted my son just to maybe like watch it, see if he'd like it. No interest. They will never know the joy of Fraggle Rock. Or Dozers. Like now, all the shows they're watching, I'm just like, I mean, they're good shows, they're educational, but now my son's like karate chopping people. And I'm just like, when I watched Sesame Street, there was no hiya. There was no Blaze or PJ Masks.
Back in my day.
All right, good to go.
Good to go.
5, 4, 3.
Hello. So, in this video, we are covering what is pretty universally decided to be one of the worst things about having to do polynomials, which is the glorious rational root theorem. So, this is really a tool of last resort, and we will see why in this video, but it is a tool to find sort of potential zeros of a polynomial. So, before we sort of dive into it, a couple observations are sort of helpful. So if we have sort of a very basic polynomial, almost as basic as can be here, right? We have a nice line, ax minus b. Well, finding the zeros for this, nicely straightforward, right? Set it equal to 0, move the b over, we get that the 0 is b over a. Pretty straightforward. If we go up sort of one level of difficulty, right, go to our nice quadratic, and we sort of saw this when we talked about the coefficient method, although this one now has some leading coefficients. But nonetheless, if we do something similar here, right, if I have this sort of, I know that this sort of nice factored form already, I set each of these things equal to 0 and sort of solve, I get that the zeros are b over a, right, from the first thing, and then d over c from the second one. Okay, big deal. Why do we care? Well, the observation that is sort of nice to make here is that in both of these cases, and in fact, this will generalize sort of very nicely, is that the zeros of these polynomials have this relationship where it involves one of the factors of the constant piece, so b in the case of my first one, or b times d in the second one. So I'm going to take one of those factors, and then I'm going to be dividing by a factor of the leading coefficient, right? So in this case, a up top, or this a times c down there, right? So in both these cases, then, these zeros of these polynomials are a factor of the constant divided by a factor of the leading coefficient, which is great-ish, right? Like, how do we use that? It's a nice observation. Why do we care? Well, let's look at sort of a concrete example, at least to convince ourselves that this thing sort of works in a more clear way, right? Like, we're not a big fan of alphabet soup. So if I have this thing, well, I can factor this, right? AC method or whatever you want to use. I'm going to get this 2x minus 3 and this 5x minus 7, which gives me zeros of 3 over 2 and 7 over 5. But again, notice, right, that 3 and 7, both of these things divide 21. 2 and 5, both of those things divide 10. This thing sort of works under at least these circumstances. All right, so with this sort of motivating observation, I'm going to go ahead and give you the sort of math version, and then we'll talk about the human version, right? The math version of the rational root theorem. So the rational root theorem, or RRT as we usually refer to it, because that's a long name, says that if we're given some polynomial, right, this very sort of generic version, but all the coefficients are integers, that's important, right? So they're all nice whole numbers, positive, negative, maybe 0. If there exists, again, I want to draw sort of real emphasis to the if there exists integers a and b such that ax plus b is a factor, meaning that b over a, or in this case minus b over a, is a 0, then a has to divide a of n nicely, right, evenly, and b divides a sub 0 evenly. So a nice sort of way of summing this up is that if we have a 0 for p of x that is a rational number, then it's going to be of the form a factor of that leading coefficient divided by a factor of that sort of constant, okay? All right, so how do we sort of use this? Well, the thing is that this allows us to generate a list of possible zeros. So it doesn't necessarily find the 0, but it allows us to sort of narrow it down from infinite possibilities to at least some sort of list. The thing is it only finds rational number zeros, okay? So for example, if we have something like x squared minus 3, rational root theorem would say that the possible zeros are 1 or 3, because it's a factor of 3 divided by a factor of 1. That gets me 1 and 3. Neither of those are zeros of this polynomial, though, right? Like, we could plug in 1 squared is 1, minus 3 is negative 2, not 0. If I plug in 3 squared is 9, minus 3, 6, not 0. And that's because the zeros of this are plus or minus square root of 3, not rational numbers, okay? So it's important that this thing only finds rational zeros. Nonetheless, that is something. So as an example, right, as a sort of concrete, fully worked out version, what if we had this admittedly annoyingly large polynomial, right? Well, rational root theorem says that we could find the potential rational zeros as factors of the constant divided by the factors of 84, which is the leading coefficient. Now, I mentioned that this is a tool of last resort. We'll see why in a second very clearly. But to be clear, we would want to try to factor this any other way we could. unfortunately, it has 5 terms. We can't do by grouping. There's no quadratic form hidden here. There's really not any other options. So we really are stuck with rational root theorem. So to do this then, well, we start by generating a list of all these possibilities, starting with all the factors of 30 and all the factors of 84, okay? So writing all those out, I have all the factors of 30, all the factors of 84. Now I want to form every possible number that is a factor of 30 divided by a factor of 84. And remember, we also need plus or minus, right? Because it could be a positive or a negative root. So if I do that, I get this monstrosity. Oh boy, right? Better than having infinitely many options, true. And in fact, it's not quite as bad as it looks because we can reduce it a little by, cutting out repeat versions, right? So for example, 10 over 2 is the same as 5 over 1, so I don't have to have that in the list twice. But that only gets me so far, right? And this really is why rational root theorem is a tool of last resort, because even sort of doing this, sure, I don't have infinitely many numbers to like throw a dart at and guess, but I still have 98 numbers to throw at a dart and guess, right? There's still a large list. And a perfectly reasonable question is, okay, which one do we choose? How do I know which of these is the right one, is the 0 that I have to use? And the honest answer is you don't. You really do, in some sense, throw a dart. Now, in fairness, as you do this a lot of times, right, as you practice this more and more, you do build intuition for some being more likely than others. But it's not a perfect system. Like, you're still sort of guessing out of those 98. A follow-up question might be, okay, what if I'm going to guess 1? What if I guess 5? How do I know, right? Well, if I want to guess 5, I could do 2 things. I could plug in 5 and actually calculate it, but doing that is kind of annoying, right? 5 to the 4th times 84, that's going to be a really obnoxious number. And the thing is if it is a 0, I'm going to want to factor anyway. So an easier way to go about this is to instead use something like synthetic division, right? So if I think, okay, well, what if, is 5 a 0, put it into the synthetic division, run it through, check the remainder. Remainder's not 0, so 5 is not a 0, right? Go back to our list, do it again. That really is how it works. So instead of 5, right, not a 0, well, let's try the factor 2x minus 3. And this is sort of useful because this is sort of a useful little subsegment here, because the factor would be something like 2x minus 3 in order for this sort of thing to look nice, right? Because that's going to have a leading factor of 84 and it has that like last constant of 30. But the 0 that I'm checking, if I'm going to use synthetic division, is actually 3/2. And this is sort of an important distinction. So if I check 3/2, well, putting it in, run through the synthetic division, aha, right? Remainder is 0. That tells me 3/2 is a 0. But that's not factoring out the 2x minus 3. That's factoring out x minus the 0, the x minus 3/2, right? Where the remainder part, this whole thing, is what I got from the synthetic division. Now, I could clean this up by factoring out sort of a nice number from the remaining part, right, from this 84x cubed bit. I can factor out something that I can cancel out the fraction over here, meaning that I can factor out a 2 from there, so that I could then multiply that 2 into the first bit, and that would give me that 2x minus 3 factor to sort of rewrite it in a nice way. And in fact, this is actually worth doing not just so it looks nice, but because when I then look at this cubic, factor by grouping still doesn't work, which is bad news for me because that means I'm probably going to have to do another rational root theorem. But because I moved that 2 over, I now have different numbers, right? I have a 42 and I have a 10 instead of that 84 and 30 or whatever, right? So as a result, I want to make sure to generate a new list, right? I want to do this factor of 10 divided by factor of 42 instead of factor of 30 divided by a factor of 84. Because A, it'll be a smaller list, but B, remember that if something was a factor before, it's still a factor now. And if it wasn't a factor like 5 before, It's still not a factor now, meaning that the list that I'm going to build is going to be a strict subset. Okay. If I have the same numbers, if I still somehow had 84 and 30, for example, I might still get the same set. So it may not be strict, but as long as I've sort of moved the numbers down somehow, I should get a strict subset. So that means that I'm going to go from this list, right, my 98 that I had before, and I can shrink it further now by using the 10 and 42 and get down from 98 to 48. So even though I've tested one unsuccessfully, which I think I actually still included in this list, so really I have 47 to check. But nonetheless, I have one that I tested unsuccessfully and one that I found. So I've done 2 tests, right? I've checked 2 factors, but somehow cut out over 50, really I have 50 plus the 5 that I didn't, keep track of. So I've cut out 51 possibilities by making this new list, right? So again, I want to really hammer home here that the idea is that you don't want to use the same list, because every time you do a step successfully, you get to cut down the list dramatically, right? But still, right, I have 48 ones to go through, or 47 if I'm getting rid of 5. So I just pick another one, right? From the new list, because at least now I know there are 50 of them that don't work that I never had to check. But still, I still have to, plug in another one. So I could try 1, again, picking numbers sort of seemingly at random. Not really, because I don't want this, video to go on for 6 hours. Turns out 1 works. What a shock. Right. So 1 works because the remainder is 0. That means that 1 is a 0. So I have, again, the thing I started with, right, the original polynomial, which I did factor 1 time into this 2x minus 3 and then that 42x cubed piece. But now that 42x cubed piece, I can factor out the x minus 1 and get down to 42x squared plus 47x plus 10. Now, you may look at that and go, but I still have 42 as a leading term and 10 as the constant term, so I haven't made my list any smaller. Which is technically true, but completely missing the point. Because again, rational root theorem is a tool of last resort. You want to avoid this at all costs. You never want to use it if you can avoid it. And guess what we have now? We have a quadratic, right? The quadratics have all kinds of other ways to factor. So you should not be using a rational root theorem to factor the quadratic. You should look at that and go, thank God, I don't need to use rational root theorem. I don't have to check 46 other numbers or whatever. I can just go ahead and factor that thing directly and get that it's 7x plus 2 and 6x plus 5. And if you're curious, I'm sure you could go back to your list and see that indeed, right, 2/7 and 5/6 were on there somewhere. And so we could have gotten these eventually, but there was no reason to go back through and start checking all of those other numbers, right? All right, so rational root theorem, this is only ever a tool of last resort. It's sort of a desperate last sort of guess measure, so that instead of throwing a dart at all of infinitely many numbers that might be roots, we're at least throwing dart at a finite, if usually very large, list of numbers that might be roots. Each time we check a factor, we want to use something like synthetic division or polynomial long division, really because A, that's going to show whether or not the remainder is 0, meaning whether or not it is a 0. But if it is a 0, then as a bonus, it gives us the factored form right away, right? Whereas if we're just plugging numbers in, it's not necessarily, right? That's not going to give us the factored form if it is a 0. So we're going to have to go do long division or synthetic division anyway, right? So this is sort of a very handy way of killing 2 birds with 1 stone in most of the cases. Plus, a lot of times synthetic division is easier than actually doing the computation, especially with large powers. Once we do find a 0, we want to extract that factor, right, using long division or synthetic division. Then we want to try to factor the remaining polynomial, the thing that we have left over, using any other method, right? Rational root theorem is terrible. I know you're going to be like, wow, this is awful. Why do we have to do this? And you're going to come to me and be like, is there any other way? I'm going to be like, no, because it really is that terrible. It really is a tool of last resort. That's why you try to avoid using it whenever you can. It's just that sometimes you really have to use it. There's just not another option. If we still need to use rational root theorem, then that's really unfortunate. But if we do have to use it, make sure that you make a new list, because that list should be a subset, which means you can cross off anything on that list that you've already checked. And usually it is a smaller subset, right? It's a strict subset. It's got fewer things to check. And to really hammer this home, don't keep using the same list. Don't check all of the options, especially when you get down to something that is like a quadratic, where there's got to be a better way, even if it's doing something like completing the square or quadratic formula or something to force out the factor. Like just don't ever use rational root theorem on a quadratic, because it's just causing you lots more pain and suffering than you need to be going through, right? Tool of last resort. Don't do it unless you have to. Okay. All right. So what did we talk about? Well, we introduced the glorious rational root theorem, which is a way of going from infinite possibilities down to a finite number of things to check for specifically rational roots. And that's sort of an important caveat, because there are polynomials that don't have any rational roots. So it is technically possible that you could have something where you have 98 rational values to check for, and you do synthetic division on all 98 and you don't find a single zero. I will not do that to you. But I am saying it is technically possible that that could happen, right? So it's worth remembering that it is only for rational roots. But I mean, it's terrible going through that many different possibilities, doing synthetic division on all of those things, or long division on all of those things, one by one, hoping you haven't made a mistake, and getting through all of that long list and wondering if it's because there aren't any rational roots or if you made a mistake on one of them, right? So this is always a tool of last resort. Try to do any other option before you do rational root theorem, because rational root theorem just takes a long time. So always go back and check. All right. So that is that.
Were you fighting back yawns?
That whole freaking time. Yeah.
Yeah, I was just like, oh, is he yawning?
Yeah. Oh, God, it was brutal.
And yeah, it's raining now, I think.
Yeah, that sounds about right.
I got like my cameras are freaking out. Stuff is happening. But it is supposed to rain like all tomorrow morning.
Oh, fun.
A whole bunch of crap coming.
That's going to be enjoyable. I have a meeting with my boss tomorrow.
It rains and pours.
Josh, I summon thee. And here he is.
Hello. Talk to me, Ghost. Quiet. Just call me a